Today we study X26NQ, Maxwell-Boltzmann distribution and specific heats. You can download the PDF file for this lecture by visiting our KPOPE digital library. The address is kpope.org, kpop.org. You can click the table of contents here, X series, scroll down to find X26, Maxwell-Boltzmann distribution and specific heats. This button brings you to the main textbook, X26, and in here you can click to find lecture, video
이번
lecture
시간에는
in Korean, and the button next to E has the link to
Today we
the
study
Korean
kinetic theory
version
of
of this
heat.
lecture, and you can click free PDF at kpop.org to return to our digital library. And if you have not subscribed to K-pop YouTube channel, then you can click here to subscribe. Okay, let's begin with this lecture, X26NQ. Find the average translational kinetic energy of molecules. Here we assume that the molecules are in thermal equilibrium at temperature T. The kinetic energy, and we assume that all of the molecules are identical molecules of mass, each mass m. We have a notation, this notation, anything regarding the a value for corresponding to identical molecules, we take the average over n molecules of something, and this value is x vector dot squared, the squared velocity. So we can be divided into three pieces, Cartesian coordinates, x, y, z components of velocity squared. So we can find the average of each contribution separately and add them up. We assume that Euclidean space is isotropic, and if we ignore the effect of gravity, there is no difference between any two axes among the three Cartesian coordinates. So these three average values must be the same. Therefore, the average kinetic energy of a single molecule over n molecules at thermal equilibrium at temperature T is just 3/2 of m and single Cartesian coordinate component of velocity squared. And we define the temperature, absolute temperature T, by this kBT equals m average value of the velocity squared along a single Cartesian coordinate. So this is the definition of temperature. So it is proportional to the kinetic energy of a single molecule, but it is not exactly the same as the kinetic energy. So kBT is 3 times 1/2 kinetic energy. But in fact, this kinetic energy assumes that there is no structure. The molecule is structureless. So it neglects the rotational or vibrational effect of a single molecule. So it's a particle assumption is hidden in this expression, in this relation. And recall the equivalence of these three Cartesian axis contributions is called the equipartition theorem. So this relation is based on the equipartition theorem. If molecules of mass m and another different mass m prime are mixed in thermal equilibrium at temperature T, then the relation holds in such a manner. So regardless of the mass, so even though its value depends on the mass of a single molecule, if we multiply the mass of each molecule, then this average value is independent of mass of a single molecule. Two, find the average rotational kinetic energy of molecules. Now let us consider the structure of a molecule. As there are two ways we assume the structure, but the structure doesn't have any vibration. So it is another simplification that a molecule is a rigid body. Rigid body. So it does not have any spring in it. So it does not have any potential energy corresponding to that conservative force. So another simplification assumption. For a rigid body, any rigid body in nature has its own three unique Cartesian axes. Mathematician doesn't know, they do not teach you any principal axis. Perhaps they teach you when you learn the linear algebra without any theoretical basis. They teach the diagonalization of a matrix, of a symmetric matrix allowed, and it is possible. But eventually, that is closely related and originates from the principal axis of a rigid body. In general, the rotational kinetic energy of a rigid body can be expressed in such a manner. Okay, what's that? This is axis of rotation. We have an axis of rotation. And if we keep the axis of rotation, then the velocity of each part of a rigid body follows this relation. Sorry. This comes from the Rodriguez formula for finite rotation. The displacement due to the rotation of an object about a fixed axis is omega cross something. So the theta dot is the angular velocity. Theta dot is assumed to be along a fixed axis and is an angular velocity and fixed axis of rotation. And velocity of each part is theta dot. So we usually use spatial notation for the angular velocity vector as omega vector. So omega cross x should be the velocity of an object fixed in a rigid body. Kinetic energy is then 1/2 mv squared, and dm is the mass of this small part and integrated over whole the volume containing the rigid body. We know this is proportional to sine theta. Cross product is the proportional to the sine theta between these two vectors. So sine theta squared is always expressed in terms of 1 minus cosine squared theta. So therefore, this cross product squared is square subtracted by scalar product squared, because it is cosine theta is hidden inside the scalar product. Using this expression, we can sum this over, we know this is the theta dot squared, vector squared, the theta 1 dot squared, theta 2 dot squared, and theta 3 dot squared. Something like that. Expand everything all together. Then at the end of the day, you will find the expansion formula, something like that. And we find that is a matrix appearing it. And we find that components of angular velocity with the different components appear in the sum of the kinetic energy. Even if we fix the rotation axis, even if we fix the axis of rotation in the expansion formula in here, for example, is a theta 1 dot x1, theta 2 dot x2, and theta 2, 3 dot x3, and we need to square this scalar product. Because of this, we have x1, x2, x1, x3, something like that. Many terms appear in this expansion. So it is impossible to avoid the crossing term like theta 1 dot and theta 2 dot, something like that. Therefore, it is completely impossible to separate 1, 1, 2, 2, and 3, 3 in general. However, nature shows us these sum can always be simplified into three terms only if you are clever enough to find a best axis of best Cartesian axis that follows the rule of nature, the physics rule. That is called the principal axis. In that case, this 3 by 3, the 9 terms will collapse into 3 terms. In addition, even if we do not make use of principal axis, once we average over the angular velocity with the n particles in n particle system consistent in gas, the average will give only squared p's only. The corresponding coefficients are called I11, I22, and I33. If I make use of a very special axis of rotation with the 3 Cartesian axes, that those choosing the principal axis, 3 principal axes to be the 3 Cartesian axes, then all of these expressions will shrink into the 3 pieces, and this off-diagonal components vanish completely. And we call this as principal values of rotational inertia. Therefore, this is a general expression, but if we choose a best Cartesian coordinate system that overlaps with the principal axis, then the kinetic energy of a rigid body molecules will be expressed in a compact way. Now, this form is very, very similar to the kinetic energy, translational kinetic energy. Instead of using mass, we use rotational inertia. Instead of using simple velocity, we have angular velocity squared. We remember, even if we use a different mass, equipartition theorem states that these values are always the same at a single temperature at which the system is in thermal equilibrium. In a similar manner, we can also apply the generalized form of the equipartition theorem to replace this average over n molecules as kBT, regardless of the value of this I. Sure, if I, the rotational inertia, is exactly 0, it cannot produce the kBT. As long as this I is non-vanishing, then this contribution, each contribution, non-vanishing rotational kinetic energy components appears, then it is to be replaced with kBT, the I times omega square along that axis is to be replaced with kBT, that is the equipartition theorem. The nature of the principal axis depends on the geometry of the distribution of mass in a rigid body. Let's see. The simple structures of molecules can be found in here. This is a single particle. If it is a single particle, so neglecting the volume of this, so I magnify this to exaggerate, but it is assumed that the size of this radius of this sphere is 0. In that case, there is no way to have non-zero value for this radius squared for this average. That means there is no rotational inertia about any of a Cartesian axis. So this results in I equals 0 along any Cartesian axis. What about this pin structure? It is similar to this. We have two atoms connected to construct a molecule. So this is a diatomic molecule. In that case, we know that we can make a rotation about this and this to have non-vanishing rotational inertia. However, if we choose the axis of rotation about the z-axis, the rotation inertia vanishes. Aha, so this, and then what about this? This is a kind of ring. We remember the rotational inertia of a ring. Even if their rotational inertia are inertias are different depending on the axis of rotation, all of the three axes will give a non-vanishing value. Okay, so we have monatomic gas, monatomic molecule, and the diatomic molecules. And then if you have three or more, whatever, from 3 on, the inertia, rotational inertia, doesn't vanish along any of the three Cartesian axes. As a result, rotational inertia about XYZ axis for a monatomic gas, a monatomic molecule, that is just a point-like system. So we have completely vanishing inertia tensor to give the three components of three principal values to be 0. If it is diatomic, just like a pin structure, we have two components non-vanishing, and the third one vanishes. So these are two non-vanishing components survive. If we have 3 or more atoms to construct a molecule, we call it polyatomic gas molecule, then all of the three principal values of the rotational inertia survive. As a result, applying the equipartition theorem for the rotation. So the rotational kinetic energy average over n molecules for monatomic gas is 0. In diatomic gas, because we have two components sub-I, so 1/2 kBt per the degrees for per degree of freedom. We have 2 degrees of freedom for the rotational axis. So we have 2 times 1/2 kBt to reach kBt, additional kinetic energy of rotation appears. In the case of polyatomic gas, we have all 3 axes of rotation, and we have 3 times 1/2 kBt. As a result, the total kinetic energy, that is a sum of the translational kinetic energy and the rotational kinetic energy, we have 3 axes of translation, and in addition, we have unknown number of axes of rotation that give rise to non-vanishing inertia and moment of inertia. There's a 0 for monatomic, and a 2 for diatomic, 3 for polyatomic. Therefore, if we include this number, so 1/2 kBt times 3 is for a monatomic gas. 3 times 2, 3 plus 2, that is 5. 1/2 kBt times 5 is the total kinetic energy, including the translation and rotational kinetic energy of a diatomic gas molecule. And we have 3 axes of translation and 3 axes of rotation, resulting in the times 6 equals 3 kBt for the total kinetic energy of a polyatomic gas molecule. Okay, that's it. Thank you.